Okay, so we've been looking for solutions to the equation AX equal to B. Remember the way that you multiply. If we assume that the matrix A can be written with columns A1, A2 to AN, and the vector X then is X1 down to XN, remember that that product is defined to be X1 times A1 plus Xn to AN. Remember, it was just the weights of the X's. The X's were the weights on the columns of A in that product. Okay, so if there's a solution to AX equal to B, then that means that B can be written as a linear combination of the A's, the columns of A. So that means that a solution exists if B is in the column space of A. Okay, so now let's say A is an M by N matrix and B is in Rn. Okay? Now, if the column space of A was all of Rn, then we know that there would be a solution. So we're going to assume that the column space does not span all of Rn. Okay? So what we're looking for is the closest solution. If B is in Rn, but B is not in the column space, is denoted by this plane here. So just so you can see geometrically what's going on here, we have a B here that is not in that column space. So that means that there is no solution to the equation AX equal B. So we want to find the solution. So of all the X's, and if you look at the products A times X, which is what creates the column space of A, all of those vectors, which one will have the smallest difference from B? So a least squares solution to AX equal B is some X bar. So they're saying that that's the X, so that A times X bar will be the value that will be the closest, meaning that if you took any other AX that's down here in this column space, those differences, the distances from B to those A's, will be greater than the distance from B to the AX bar. So the X bar will be the least square solution if B minus AX bar will be the smallest size. Okay, so that'll be the shortest distance from B to any other AX that's in the column space of A. Okay, so we're looking for that value that's the closest to B. Okay, so the X bar, though, it will be the actual solution. Okay, so that's what we're looking for, is what is the closest solution to the equation AX equal B if there is no actual solution, meaning B's not in the column space. So we want to find that, and it will be that B is the projection onto that subspace. Okay, so we have a vector B here. We're going to project that onto a subspace, the column space of A. Okay, so this B hat then would be the closest point in the column space to B. Well, since it's in the column space of A, that means that there's some X hat that's in Rn, so that A times X hat is equal to the B hat. Okay, so B minus AX hat then we know will be that shortest distance if you consider B to any other AX in that column space. Okay, so we know that B minus the AX hat is going to be orthogonal to each of the vectors that are in the column space. Okay, remember this B minus AX hat is in the orthogonal complement of that subspace. Okay, if it's in the orthogonal complement, that means if we take each of the vectors in the column space dotted with that vector, so some of the things in the column space of A are each of the A's that are the columns of the column space. So if we said that A was equal to A1, A2 to AN, each of the A's is in the column space. They're clearly a linear combination of that set of vectors, just one times each column. So we know that A sub I A sub 1, A sub 2, A sub n, all of those A's dotted with that vector b minus ax hat will be equal to 0. Okay, and that's because this is in the column space of the orthogonal complement of the column space. And that's just going back to when we did the projection and then found the difference, b minus that projection, which was orthogonal to the projection itself. Okay, so now that's true for each I, for I from 1 to n. Now another way to write that, instead of putting it as a dot product, we can also write that using transposes. That means that AI transpose, we can think of it now as a multiplication, a matrix multiplication. So b minus ax hat times AI transpose, so now we're doing a matrix multiplication, will be equal to 0. Now that's true for each of the I's. So that's true for each of those columns of A. Well, if that's true for each of the columns of A, or the rows, if you take the transpose, that means that if we took the matrix A transpose, it also will have a product times this b minus ax hat of 0. Okay? So if it's true for every column of A, it's going to be true for the A itself. Okay, so this is equivalent to A transpose B equal, or minus, one step at a time here, A transpose A times x hat, which means that A transpose times B is equal to A transpose times A times x hat. Okay, this is called a normal equation. Okay, normal meaning orthogonal. Okay, so the set of all solutions to the least square solutions, we're looking for the solution x hat, okay, which are equal to that b hat. So that's going to be that least square solution. Okay, so it corresponds to the x that would have that product ax hat that equals to the b hat. Okay, so the set of all the least square solutions of ax equal b coincides with the non-empty set of solutions of these normal equations. So if we're trying to find the x hats so that this is the ax hat is equal to that projection of b onto that subspace, we can get that by solving these normal equations, okay, which will be a lot easier than trying to figure out what that closest solution is and what the x is that satisfies and makes that projection. Okay, so I want to find a least square solution of the inconsistent system ax equal b. So inconsistent meaning there is no solution. That means b is not a linear combination of the columns of A. Okay, so let's get our formulas. We know the normal equation is A transpose A times x equal to A transpose times b. Okay, so let's form the normal equations. I need A transpose times A and then times x. So A transpose times A okay, so we'll get the 2 by 2 matrix, 17, 1, 1, 5. Okay, now let's try A transpose times B. We're expecting a 2 by 1. So we'll have 8 plus 11 is 19 and 11. Okay, so now we want the solution to the normal equation. We're trying to find the x that satisfy this. So that means we want to know the solution, 17, 1, 1, 5, times the x that equals to 19, 11. Okay, so now to find this solution, so x will be the solution which corresponds to the least square solution of this equation. So to solve this, we can either row reduce the augmented matrix, or because I see that this matrix does have an inverse, a quick check, the inverse of it does exist. So let's find the inverse. So that means that x is going to equal to that inverse. Well, the determinant of that is 84, so it's 1 over 84. Swap the 5 and the 17 and make the others negative. So this is the inverse of this matrix to the left of x. And then we just want to multiply that by 1911. Okay, so 95 minus 11 would be 84. And then 187 minus 19, 168. Okay, so that's our least square solution. That's saying that that vector, if you take a times x, that will be the closest possible, solution in AX, in the column space of A, to 2011. So that's our least square solution. Okay, and we'll work with that a little bit more later. I want to find the least square solution of AX equal B. Notice that last example, we had a unique solution. Okay, you don't always have to have a unique solution. There may be a whole set of vectors that are just as close to the vector B. Okay, so we're going to do the same thing. We're going to look at the equations. A transpose AX equal to A transpose times B. So we'll look at forming the normal equations. This is A transpose times A Okay, so we expect to have a 4 by 4. So we'll have 6, 2, 2, 2. Row 2, 2, 2, 0, 0. 2, I'm on row 3 now. 0, 2, 0. And then 2, 0, 0, 2. Okay, so that's your A transpose times the A. Now let's do A transpose times B. No, I'll just do it over here. Okay, so I expect a 4 by 1 here. Just add all of them. 4. Add the first 2 is negative 4. Third and fourth is 2, and the last 2 is 6. Okay, so now we have A transpose times AX equal A transpose times B. So set up a system. times the vector x. Okay, so this one we're going to solve by setting up a system of equations. Okay, so the augmented matrix okay, we'll reduce it. Okay, so just RREF with your calculator. Now we'll see that there's a free variable. Since you have a free variable, you know you have an infinite number of solutions. So we have that x1 is minus x4 plus 3. We have that x2 is equal to x4 minus 5. We have x3 is equal to x4 minus 2. And we have that x4 is free. So if we want to find the vector x, we can write that as 3, negative 5, negative 2, 0, plus x4 times negative 1, 1, 1, 1. Okay, so we just found an infinite number of solutions for that least square solutions. So there's not always just a unique single value. So this is giving us all the points, all the x's that are in Rn, so that a times x is the same distance to the vector b. Okay, so if you wanted to have just any solution, you could pick x4 equal to 0. So one solution, least square solutions, not a solution, is just 3, negative 5, negative 2, 0. And then plus any multiple of the other. Okay, so this is the form of all the least square solutions. Now notice I did two different ways to solve this. I started with the normal equations, but in one case we had a unique solution, in the other case we didn't. So now there's some criteria in this next theorem that actually tell us when we will have a unique solution. So if A is an m by n matrix, these statements are all equivalent. Ax equal b has a unique least square solution for each b in Rm. That's going to be true when the columns of A are linearly independent. And that's going to be true, which of course also meant that if you had an n by a square matrix, that would mean that the inverse existed. Also, the matrix A transpose A is invertible. So if A transpose A is invertible, then we'll know that there's a unique solution. So we had the equation A transpose AX equal to A transpose B. So if any of these conditions were true, in other words, A transpose A was invertible, that means its inverse exists, or the columns of A were linearly independent, that would mean that A transpose A also was invertible. That would mean then that we could solve for X by just taking A transpose A inverse of both sides. So if I just apply that to both sides on the left side, this would be my unique solution. So that would be the unique least square solution. Okay, but when it's not unique, you'll have to solve it using the augmented matrix and get that general solution like we did in the last example. Okay, so one more problem on this. When a least square solution x bar is used to produce that approximation to B, the distance from B to that AX is called the least squares error. So that tells us how far off that solution is to the desired B that we would have wanted to have, for the equation. So in example 1, we found that the least squares solution was x bar, which is 1, 2. Okay? I want to find what is the least squares error. Okay? Well, the least squares error is equal to the magnitude of B minus the AX bar. AX hat. Okay? So if we just find that magnitude, then we'll know what the least squares error is. So if you took any x times a and found that distance between that product AX and B, it will be greater than it will be for the x 1, 2. Okay, so first thing we need to do is to find AX hat. Okay, so this is going to be a 3 by 1. It'll be 4, 4, 3. Okay, so now let's find B minus AX hat. Okay, so the least squares error then is the magnitude of that vector. Okay, so that's the least squares error. So no other x chosen will have a smaller error. So let's just check one. Okay, so that's your least squares error. So just as an example, let's pick another x that's in R2. So let's look at AX. Let's pick something close to 1, 2. Let's pick 1, 1. So that will be 4, 2, 2. So now what would the difference between B and that AX? Well, B minus that AX which is slightly bigger than the 84. Okay, so if they ask for the least squares error, find the least squares solution, and then just take the magnitude, that distance between B and that AX hat.